Welcome to Lesson 11, and Lesson 11 begins our Unit C, which is Ratios and Rates Involving Fractions. Okay, and Lesson 11 attends specifically to ratios of fractions and their unit rates. Now this is it's going to be challenging for some, probably for most, and a little bit time consuming because fractions do take some more time to work with. So we are going to look over this question, this example 1, who is faster, and I'm going to have you pause the presentation and then go ahead and try to solve it in as many ways as you can, and I'd like for you to try multiple ways, just because this will serve as a checking mechanism. Okay, if you get the same answer both times or the multiple times, then you can be more sure that that your answer is correct. And when you come back, I'm going to go ahead and go through a number of ways to solve this problem, and we can do that together. Okay, so good luck. Okay, well, first thing I want to suggest is when you're dealing with minutes, it'd be really nice to, and again, if you're having any struggle with this, it's just to have the reference of a clock nearby, okay? Because when you do have that reference of a clock, you do notice something, that 15 minutes happens to be 1/4 of an hour, okay? So this here is 15 minutes, 1/4 of an hour. You're dealing with 15 over here, then you're dealing with 25. That 25 can be broken into fives, and every 5 minutes, if I did break everything into fives, every 5 minutes right there, because I have, so if, this entire thing here is 15. Each one of these is going to be 5, and each fifth is going to be 1/12 of an hour. It's 5 minutes, and it's 1/12 of an hour. Okay, and again, I'm not sure how much that helps, but if you're going to work with fractions, just to understand that. Okay, have a clock handy. Maybe that'll help you out. Also, with this problem, you know, it is really sloppy or confusing, but we have to do it. Work with these fractions, okay? But it can be a little bit difficult. But if we just went and changed these numbers, just really quickly, just let me say, instead of saying 2 1/4 miles in 15 minutes, why don't we just say 2 miles in 15 minutes? Okay? And if we were to say over here, instead of 3 3/4 miles in 25 minutes, let's just say 4 miles in 25 minutes. Okay, and again, just evening these out, almost like kind of rounding the mileage number, just so we know. Because when we're trying to create a ratio now, we are, again, if we look at our x and y. Okay, so our x and y, and again, independent variable, dependent variable. All right, and here we have our independent variable is the miles, right? Because we have two miles here. We're going to use this new example right here, 2 miles, and the dependent variable is 15. Okay, and again, the x and the y. What do we do with this? I mean, we go ahead and we could put y over x. Okay, so we are coming up with here. We're coming up with a minutes per mile, because we have minutes on top, and it's a rate, okay, a very popular rate, minutes per mile, or, you know, I mean, miles per minute as well. I mean, it can go either way, all right? But if you're trying to get this down to 1, we're trying to find out for every 1 mile, how many minutes does it take us, and that would be 7.5 minute miles, okay, minute mile. Minutes per mile. Okay, all right, and it's a little bit easier because we have this whole number here now instead of this here. Okay, this fractional number. So if we just, so we had that, so if we did that, that's 7.5 minutes per mile. We do the same here, recognizing that as 25 over 4. 25 divided by 4 is, what is that, 6.25, right? Yeah, 6.25. 6.25. That's right, 6.025. Let me just see here. Let's just actually do it, huh? How's that? Because then we have 6, and then we have 24. 1, right? And then 2, yeah, 6.25. So 6.25 minutes per mile. And in this case, if these were the real times, you can see that this girl here, which would have been Julia, okay, would have been the faster runner because she's running a mile in less time. It takes her only 6.25 minutes, which is a decent mile. Both of these are decent miles for me anyway. Okay, but again, this is just using, just so you know that, don't confuse yourself, because if you're getting this, you know what these numbers mean, you know where you need to put them in the ratio. Just go for it, okay? They're sloppy, they're ugly, they're fractions, but make it work, okay? So let me go ahead. I'm going to sweep this clean, and let's go ahead and look at it a few different ways. Let's first thing we do, let's go ahead and create a table for this problem and work it out. And again, the answer is not necessarily Julia is the faster runner, simply because I rounded those numbers, and it could be, because I rounded Izzy's down that time, and I rounded Julia's up. So that's really not very fair, huh? So yeah, we're going to go ahead and create a table first and solve the problem. So the first way I want to show you to how to solve this problem, I mean, it's not always going to work, but if you do notice something about some of your numbers, for example, I'm looking here in the time area. I see here with Izzy, I have 15 minutes, and I'm going to use those as like 15-minute increments. Okay, so I have, in 15 minutes, I know she went 2 1/4 miles. When I look over here at Julia and I see 25, and then I have 3 3/4 miles, I know that there is going to be, and again, every two numbers is going to have a common multiple, and that's when you multiply those two numbers by each other. But in this case, with these two numbers, I know, because I know my multiplication facts well, I know these two numbers have another quicker, sooner to be found common multiple. Okay, so what I'm going to do then is I'm going to use these increments. So if I know, and again, this is all about the constant. Okay, so, and it's all assuming a constant. Okay, because we are making a big assumption. People do not necessarily run consistently the same speed when they run a race. Some do try to pace themselves well, but there's always that that sprint at the end, or that somewhere in the middle, or maybe even at the beginning. But anyway, we're going to assume a constant rate. We don't even need to actually figure out this rate right now. Okay, but we know that for every 15 miles, every 15 minutes, she runs 2 1/4 miles. Okay, so therefore, in 30 minutes, she's going to have run 4 1/2 miles. Okay, and I hope you can see how I get that. Okay, because if I'm going down, if I'm multiplying this by 2, multiplying 15 times 2, in ratio, remember both sides need to be multiplied by that same factor. Okay, so here we go. I multiply 2 1/4 times 2, and I get 4 1/2. Okay, 30. 30 is not, they're not common yet. 30 and 25. Let's get the let's do it for Julia's side. If I multiply this by 2, okay, and it's the easy thing to do, I get 50. Okay, so now in 50 minutes, Julia would have gone, what's that, 7 1/2 miles, right? Okay, because 3 plus 3 is 6, and then 3/4 plus 3/4 is 1 1/2. 6/4 or 1 1/2. Add those, 7 1/2. This kind of stuff needs to be quick, though, and if you're not getting that, I can't spend a lot of time on how to just double fractions. Really got to work on that and know that, okay? So that's 7.5. So we still do not have a common multiple yet, okay? Let me go up again here, another 15. That's going to bring us to 45 on this side, okay? Again, I'm sorry, I'm not doing that. I want to go ahead and, yes, I am going to do that. Let's go ahead and do that. So if I go ahead and another 45, so that's going to be another 2.25 miles. Okay, she's gone another 2.25 miles. So that's going to be then 6 3/4 miles. Okay, so now in 45 minutes, again maintaining that ratio. Okay, these are all equivalent. Okay, all right, because now I am using this one here to go. So I'm adding not only doubling here, but actually multiply. I'm just adding or just continuing this 15 to 2.25. Okay. On this side, 75. Okay, 75 is another 3 3/4 miles. Okay, so because for every 25 miles, she's going 3 3/4 miles. And if I go ahead and do that, that's 10. It's going to be 11 and 1/4 miles. Okay, you can see 11 and 1/4 miles. Because what I've done is I've added another 3 3/4 to 7.5. Okay, because again for every 25 minutes she goes 3 3/4 miles. So this one and then times this one. Okay, all right. So now I notice something, and 75 is the key right here, okay? Because if I have 45, if I go up another 15, that is 60, and then I know if I go up another 15, that's 75. So we have a common multiple. We come to a common multiple right there. But let's go ahead and continue this process, because now we had 6 3/4 miles at 45 minutes, and then another 2 1/4 right there. That's going to be what, 9 miles even. Because again, for every 15, okay, I'm going up 2 1/4. Okay, so right here I'm adding another 15 here, so I had to add another 2 1/4 miles to this, and I get 9. Okay, again 75, and then we add another 2 1/4, and we get, lo and behold, look what we get. We get 11 and 1/4 miles. And what do you notice here? That Izzy, in 75 minutes, goes 11 and 1/4 miles. Okay, Julia, in 75 minutes, goes 11 and 1/4 miles. Okay, so in this case, if we're going to find a common denominator, in this case, you can tell. It's very difficult to tell at any given point here. You can't tell at 15. Izzy at 15 here. You can't tell. You can't compare her 15 minutes to her 25. Okay, in this case, you can't compare this 30 to this 50 because these are all different times. All right, all different times until you get to the point where you hit the 75, which is a common multiple. You hit that 75. So at 75 minutes. If these girls are going the exact same distance, and they've gone a constant rate this entire time, you know they're going the same speed. Okay, because then, if we wanted to, okay, we won't do it here with this table, but we will in the next couple of ways that we try to solve this. We will go ahead and get an actual rate. Right here, right now, we're not shooting for a rate. We're just looking. We went to find out how can we really compare these two. The only way we can compare these two head to head is when they have gone the same amount of time, and that happens to be at 75 minutes. So at 75 minutes, they have gone the exact same distance. Okay. We could have looked at a common distance as well, and we did actually. We got 11 1/4 miles. They both went that, and they both go the same time. Now, if it turned out that at 75 minutes they both hit 75 minutes because that was a common multiple, because we were using the multiples just because it's easy. Okay, just you use the factor of 15 because it was easy, factor of 25 because it was easy, and because I knew anyway that I was going to hit a common multiple at one point. Okay. All right, so let's go and let's handle this a little bit differently. Now, if we go ahead and try to calculate a unit rate just using our numbers that we have here, because we can do that, okay? There are a few different ways we can try it. Our unit rate could be many different things. It could be, for example, miles per minute, and that would be here. If we went ahead and put together a fraction or a ratio. Miles per minute, we would be 2¼ miles, 2¼ miles divided by 15 minutes, because we're trying to find out again how many miles, in this case, per minute. All right. I'm not sure what I just did there. Miles per minute. Okay. Now in this case, we've changed our x and our y. We now have miles as y and minutes as x. Again, in this case, dependent, independent does not matter all that much, because you can set out to run a 2¼ mile race, or you could set out to run 15 minutes. So it could be either or, and hopefully that makes sense to you. Sometimes independent and dependent variables, it's very, very clear which one has to change. But hopefully you can understand that if I were to run a race or just go out and run, okay, and I do run, I may set out to run 6 miles. Okay, so my goal is 6 miles. Then that is my independent. In this case, I'm going to run 6 miles, and then however long it takes me, whatever it takes me, maybe 48 minutes, okay, then that's my dependent. Okay, it depended on how many miles I actually ran. But I can also say, hey, I'm going to go out and run 30 minutes, and that becomes my goal. Okay, I'm going to run 30 minutes, and here is my, this would be my independent. Okay, I'm going to run 30 minutes, and then my dependent was how many miles I actually went. Let's say, like, I don't know, maybe 4 miles. Okay, then that becomes my dependent. So hopefully you see what I mean. The x and the y in this case is not so important. But when we're talking about speed, we very often Americans generally talk about speed. We talk about miles per hour. Okay, now when we talk more scientifically, we talk about the rate of gravity on Earth. We talk about usually meters per second. That's something else. But if we're going to do speed in maybe more scientific applications, such as sound, the speed of sound, or the speed of light, we usually talk about meters per second. Okay, but anyway, let's go ahead and do miles per hour here. Okay, I want to focus on that. So what I've done here is I've gone ahead and made this ratio, and here is of course, our division symbol here. Okay. We are going to do miles. Now, what I did is I went ahead and changed 2¼ miles to 9/4 miles, which is 9/4. Okay, so I'm trying to get these, both of these fractions, the fraction that is serving as our numerator, which is 9/4, and the fraction that's serving as our denominator, to look the same. Okay, to both themselves have a numerator and a denominator. Okay. Now I am changing 15 minutes to 15/60 hours. Okay, and hopefully you can see how I get that. We talked about the clock before. Remember, 15 minutes is, the whole thing is 60 minutes, right? We go all the way around the clock. That's our whole. And then we're talking about 15 minutes, so we're talking about 15. Now, if you notice something else, if you remember or recall or just knew this anyway, 15/60 of an hour is actually 1/4 of an hour. Okay, so this actually equals 1/4 of an hour. All right, so we've actually reduced that or simplified that to 1/4. All right. So now what we are left with is we have 9/4 over 1/4. Now, there are many different ways to look at this, because when we talk about division as a concept, as an idea, we are always asking ourselves, how many of one thing are there in another thing. Okay? For example, 30 divided by 5 is going to ask, how many of these 5s can I fit into this 30? And we know that that is 6. Okay, so if I had 30 of these, how many groups of 5 would there be? We circle them all and they would end up with 6. Okay, so that idea, very, very important. And the way it works in this sense, when we look at fractions like this here, that we've drawn right here, and this is not very common to most of us, to look at fractions this way. We're always used to fractions having just a numerator and a denominator, okay? So we talk about algebra now, we can create fractions that are fractions over fractions, as you can see here, okay? But what this looks like in a more traditional looking division problem would be 9/4 divided by 1/4. Okay, that's what that would be in a more, and you'll see this problem look that way, and you have in the past seen it look that way. In algebra, you're going to be seeing them more and more like this. Okay, more and more this idea. Okay, and what is this asking us? Well, just like the problem prior with 30 divided by 5, how many 5s are there in 30? Here we are asking how many 1/4 pieces are there in 9/4? How many of those are there? How many 1/4 fit into 9/4? And hopefully you can see that right away, and I know some of you can, but if we look at a picture, okay, I could draw, let me make 9/4, I'm going to make some rectangles, 1, 2, okay, that's 4/4, another 1, 2, that's 8/4, and then I'll make another big piece, but here's our last fourth, there's our 9/4, okay, so here we are, here's our 9/4, okay, we're assuming these are all holes, here's 9/4, okay. Now, how many 1/4 pieces, here's a 1/4 piece, because we can see each one of those is a fourth, how many of these are there in these 9/4? There are 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So the answer would be 9/4 divided by 1/4 equals 9. Because there are 9 1/4 pieces in 9/4, as we see here. 9 of these are in this 9/4 right here, because that's 9/4, or also 2 1/4, which is what we've been working with. Okay, so if we go back to our problem here, so 9/4 miles divided by 1/4 of an hour equals 9 miles per hour. Okay, because what we've done is we've created our unit rate. 9 miles per hour. So our first girl, Izzy, ran 9 miles per hour. A nice even number, which is very, very friendly for us. Love it. It's not always going to be that way. Yeah, that's one thing about you as you move forward working with fractions and algebra. Things get sloppy, and you've got to be ready, but don't be confused. You know what to do. Do it. You know you're trying to figure out 9/4 divided by 15/60. Just do it. Do it the best way you can. Okay? 9 miles per hour. Okay. So let's go ahead and look at Julia then. So Julia now is 3 3/4 miles in 25 minutes. Okay, so maybe look a little bit different, maybe not as friendly. Let's go ahead and create our ratio, or our fraction of fractions, right? So 3 3/4, we want to make this into an improper fraction because, again, it just like we did with the 2 2/4, because we can work with these much better, they become more understandable. Okay, 12. What's that? 15/4. And you saw how I did that, and hopefully, again, I don't want to have to be teaching you these things for the first time. I'm hoping that you know it. If I know if I have 3 holes, okay, I have 12 fourths, that's this 3 here. Then I just add those 12 fourths to the 3 fourths that I have extra here, and that gives me the 15 fourths I have here, okay? So 15 fourths. Now 25 minutes is 25 over 60, okay? And I can reduce this. Again, right away, you're sharp with your frac, you're sharp with your multiplication facts. This is why this has been so important all of your lives. I know many of us didn't quite get it. We can see that we have a common factor here is 5, and that would be 5/12, okay, because that is the same. These are equivalent, okay, so I've just divided 25 by 5 and 60 by 5, okay, all right, so 5/12. So what we're looking at then, we're looking at this. We're looking at 15 fourths miles over 5/12 minutes, okay? Or, sorry, not 5/12 minutes, because we've actually changed this to hours now, because that's why we did that conversion, okay? Because we converted. Again, remember, when we're turning this minutes into hours, we're just creating a fraction, because we need that 60, because the 60 minutes is our whole hour, okay? So 15 fourths miles over 5/12 hours, okay? And so again, 15 fourths. So what would it look like in a traditional way? 15 fourths, therefore, divided by 5/12, okay, equals, all right? Now, if we do our model of like we did here with using our, there it is right there, okay? This was very convenient because if you look at here, makes this so much more doable is that we have fourths here, we have fourths here. How many 1/4 pieces are there? 9 fourths. That becomes a heck of a lot easier. We need to do no conversions whatsoever. But here, if we're going to work with this in that same way, we need to convert. Okay, so we need to convert we need to change one of these denominators. But again, this is pretty convenient because we can see a common multiple, or the least common multiple of 4 and 12. Hopefully you can see this quick. It is 12, right? Okay. Okay, so if we have 15 fourths, okay, because we're multiplying this 4 times 3 to get that 12. We're going to multiply this 15 times 3 to get our new numerator, which is going to be 45. Okay, so now we can go 45, I don't know what happened to my thing here. Oopsie. 45/12. I'm having trouble with my... Okay, I'm sorry. I'm not sure what happened there. I got disconnected. I think my my laptop here timed out. So I'm not sure exactly how much you got of this, but what I was saying before I got cut off was that when and I may be repeating myself, and I'm sorry if I am, but when we went ahead and we found the 9 fourths of how many 1/4 pieces there were in 9 fourths. That was quite easy, okay, because we had common denominators right away. Okay, in this case though, we don't have that, but we do need to make common denominators if we want to do it this way. Okay, because there is another way, another kind of cut to the chase way, which some of you are thinking, hey, why doesn't he just do this? Get this over with, pal. But anyway, let's go ahead and do it this way, because I want to see, I like that you see this idea, because when we're dividing, when we're finding out, when we divide 9 fourths divided by 1/4, we are trying to find out how many 1/4 pieces do fit into this 9 fourths. Okay, just like that, we're doing the same here. Our common denominator is 12ths, okay, and hopefully, I think I said that before, I'm not sure if you got that, but, and this would be 45/12ths, okay, because again, we're multiplying by 3 to change 4 to 12, so we have to do the same with the 15, okay. 15 times 3 is going to equal 45. Okay, so now we are asking ourselves, and again, hopefully this is popping out, we're saying 45/12ths divided by 5/12ths. Boy, does this look familiar? Remember before we had 9/4 divided by 1/4? And what do we have to do really? If we had the same denominator, all we had to do is do what? Look at 9 divided by 1, and that equaled 9. In this case, if we're going to find out how many 5/12 pieces there are in 45/12, we could do the exact same thing. 45 divided by 5 is 9. But again, to prove it, why don't we just go ahead and look at it? If we have 12ths, 1, 2, 3, 4, 5, 6, let's say this is 12, okay? 12, and then another 12, was that 24? That's 36. 36 12ths. How many 12ths do we need? We need 45 12ths. So we need another 9. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay. So we have right here. We have 12 12ths right here. Okay. Here's 12 of those 12ths. Okay. And then here's another 12 12ths. That's 24. 36. And there's another 9 12ths. That's 45. Okay. So if we're trying to fit 5 12th pieces, and this right here is 12 12ths, we get 5, and then another 5, okay? That's 1 5. That's another 5, okay? Actually, we should probably just count them. Let's go ahead and do this here. Let's go ahead and say here is, so here's 5 12ths. There's another 5 12ths. That's 10 12ths. We have 2 left over here. Okay, so we get that out of there. Then we have another 1, 2, and then another 3, 4, 5. That's another 5, so that's 15. And then we took 3 out of that, another 5, that's 8 over here, and that's 20. And then, so 8, and then 20. How many do I have here? Another 4, another 5 here, that's 25. Another 5, 30. Another 5, 35. And then another 5, 40. And then we got 45. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of those groups. 9 groups of 5 12ths can be taken from 45 12ths. Okay? Again, if you get that denominator common here, all you need to do is to divide these numerators. Okay? All right? So, and again, we can see they both went 9 miles per hour. All right? 9 miles per hour. Okay? And again, we've proven, just like we did before, that they went the exact same speed. But let's go ahead and look at this 15/4 divided by 5 12ths. And let's go ahead and look at them both. And look at the other one too. Let's look at these a different way. And it was 9/4 divided by 1/4. Again, Izzy, one Julia. Okay? Now, I think it's really important that we do understand what we're doing. We're doing messy things like that. We are doing this always, okay? We're trying to find out how many fractional, this fraction is in this fraction, okay? This is the way it's more conceptual. It's what you're actually asking yourself. But there is an easier way. And that's when you are doing division. I know some of you know this already. What division is it is what we call the inverse of multiplication, okay? It's the opposite, okay? So because of that, you can create a new equation here. Your first one has to stay the same because this is still our whole here, okay? Still our whole. But now, instead of dividing by the 5 12ths, we are multiplying by the inverse or the reciprocal, okay? And here we'll do the same, okay? And if we do that, okay? This looking familiar to you? So we've actually changed these into their reciprocal or their inverse, okay? And then if we go ahead and do this, you can see we can do what's called, this cross here. We have this 4 and this 4 cancel out. They become 1 each. 9 times 1 is 9. 1 times 1 is 1, and that, of course, is 9. Over here, we can do the canceling as well. That becomes 3. That becomes 1 because we're dividing by a common multiple. Okay, 5. And here, too, the same. Now we're going to multiply or divide by 4. That's 1. This is 3. 3 times 3 is 9. 1 times 1 is 1. and again we get 9 miles per hour. Okay, we can look at this problem as an equation. We can create an equation as we had at the end of our last unit, and which is what we need to do more and more moving forward, okay, is to create equations. Now, the one equation, or this one ratio right here, is a very, very important one you'll be working with in science as an 8th grader, and things that you'll see over and over again in problems that we face in math. But it's D equals RT, which is distance equals rate times time, okay? It is speed, okay, our speed formula. So, speed or velocity. Izzy and Julia, we are both going to plug in their numbers, which are up here. Okay, we're going to plug their numbers in using this formula, D equals RT. Okay, now distance, we know for Izzy was 2 1/4. 2 1/4 miles. Okay, so let's just go ahead and work this out. 2 1/4 equals R times T. Julia, we had 3 3/4 equals R times T. And again, you know, some of you working with these types of things for the first time, but you are, you place two variables next to each other, the R and the T, and that is assuming a multiplication. Okay, there's no need for a dot in the middle, an X, not even a parentheses. So sometimes you use them, look different at different times, but just to know that this is R times T right over here. And again, I've kind of made that known over here. Okay, so if we continue to plug in, the other thing that we know is with Izzy, we know her time, and we're going to say 2 1/4 equals R, which is what we're solving for, because we're trying to find their rate. Okay, we are trying to uncover the rate of each girl in terms of miles per hour. We're coming up with a mile per hour rate. Okay, but we also know her time, which was 15 minutes. Now, again, to make this a little bit more easy to work with, I mean, you could put 15/60ths, but you know, as we found out before, that is the same as 1/4. Okay, so 1/4. Okay, and again, this is now we need to have our dot here. Okay, and now with Julia, we know we can plug in our time. 3 3/4 equals rate times, and we know from the work we did before, that was either 25/60ths, or we also had 5/12ths of an hour. Okay, so this 5/12ths, again, and we've done this before, but just to reiterate, this 1/4 is the fractional representation of this 15 minutes in terms of hours. So 15 minutes is the same as 1/4 of an hour, quarter of an hour, okay? And then 25 minutes is the same as 5/12ths of an hour, okay? So again, these are fractional representations. They're going to work well going forward in this equation because we already have fractional miles, or fractional distance here, okay? Now, I'm not sure how many of you remember how to proceed forward, but if you do recall at the end of our last unit, when we're trying to solve for R right here, we need to isolate R. We need R to be all alone on one side or the other. Okay? So the way to get this R to be on one side by itself is to divide this whole side here by 5/12ths. And this whole side by 1/4, because we know that if we divide 1/4 by 1/4, that's going to be 1, because that is a rule, okay, is a rule that we know any number divided by itself is 1, okay, or positive number, positive rational number, okay. 5/12ths divided by 5/12ths is 1. Okay, so what we're actually saying over here, we are saying r times 1, which is r. Okay, and over here r times 1, which is also r. Okay, so now we have an equation that is going to go forward looking like this. So 2 1/4 equals r, and then 3 3/4 equals r. Now, there's one step here that we haven't yet done, and this is a major, major rule, and some of you may have caught this already. Hopefully you have. Whatever you do in algebra on one side, you need to do on the other, because algebra is a balance. Okay, so let's go ahead and get a new page here. See, 3 3/4 equals r, and then we have 2 1/4 equals r. Now again, to get this little equal sign here is like, is like the fulcrum on a balanced scale. Let's say it's in between. What we did to get this r right here was we divided by 5/12 on this side, we divided by 1/4 on this side. Okay, therefore, we need to do the same on this side and the same on this side. So what was that number? That was 5/12. Okay, all right. So because we to get this r here, remember we divided by 1/4. To get this r here, we divided by 5/12. We need to do the same on this side. Now this, hopefully, looks very familiar to you. Okay? And this does as well. All right? If we go back and we look, we have our 9/4 divided by 1/4. And then we had our 15/4 or divided by 5/12. Okay? So we go forward, these are the exact same problems. So then we can do it. We have our 15/4 divided by 5/12. We have our 9/4 divided by 1/4. And again, you know what that is. That is the same as saying 9/4 times 4/1. And 15/4 times 12/5. And you remember what happened when we did this? We ended up with 3, 3, 1, 1, 9 here, and we ended up with 9 over here as well. Okay, so 9 miles per hour. So with an equation, we have proven that both girls ran at the same rate, and that is a major assumption. And that is what we are assuming in this problem. Again, not reality. Very, very difficult for any human being to run the exact same rate the entire way around a track. But that's what we are assuming here. And as you can see, again, we've proven that they ran at a similar rate. Okay, now there probably exists several other ways you could have figured out our Izzy and Julia problem, and you may have a procedure yourself that you might want to share with the class, and I'd love that if you did. Again, we are trying to move more and more towards the use of things such as complex fractions, as you can see right here in this problem. And let's go ahead and just, let's do this problem. Let's work with this and get closer and closer to becoming more and more comfortable with working with fractions, and not only just fractions, but working with them as complex fractions, which is, fraction on top of fraction. So here's our exercise. A turtle walks 7/8 of a mile in 50 minutes. What is the unit rate expressed in miles per hour? Okay, so we're going for the miles per hour. Okay, we're given the minutes, we're given the mile, we're given miles and miles per minute, not miles per minute, but miles in minutes, but we need miles per hour. Okay, so now AS says right here, it says to find the turtle's unit rate, Meredith wrote and simplified the following complex fraction. Okay, so what this question is asking you is not asking you truly to do any kind of calculating, but it's asking you, where did she get this fraction 5/6 from? This one right here. Okay, so I want you to pause, take a look at it, spend some time seeing where she might have gotten that 5/6, which exists on the bottom of that complex fraction, or as that complex fraction's denominator. Okay, again, so the question was, how was the fraction 5/6 obtained? This one right here. Okay, so when she's trying to figure out miles per hour, what Meredith first did well was she put her miles as her numerator. Okay, and then on the bottom of her complex fraction, she might have started with 50/60ths, because we were talking miles. This is miles, and now I've turned this 50 minutes into a fractional portion of an hour, okay? Because a whole hour is 60 minutes, and then the part we have here is 50, so 50 over 60, okay? Now she could have originally written it this way, but what she did correctly, and where she got this 5/6, and you can see, is that she simplified 50/60ths, which very simply becomes 5/6. Okay, so she did that, and yes, indeed, she did that correctly, but I guess that was already assumed, but you can see where it came from. It actually came from the fractional representation of the minutes as a fraction of an hour, and then that was simplified. Okay, so B asks you here, did Meredith simplify the complex fraction correctly? So you can see what she's done here. She's simplifying this, and what she's done is she's used this little method. And if you look at that, I want you to go ahead and do any kind of calculation that you think you may need to, and tell me if you think if she simplified this complex fraction correctly. Okay, so before I answer that question or start looking at whether she simplified that complex fraction correctly, let's take a look at what Meredith was doing when she originally wrote her 7/8 and created her complex fraction this way. Okay, we know what she is doing is she is dividing the 7/8 by 5/6. Okay, now very simply, what she could do is then create her equation this way, and we know by now that what we're trying to do, we're trying to find out how many 5/6 there are in 7/8, and because multiplication is the inverse of division, what we do then is we create a more reasonable or easy to work with algorithm here, and we are going to go ahead then, remember, we take the reciprocal or the inverse of the second fraction in this equation here. Okay, so now this is what she's attempting to do. Okay, she could get her answer this way, okay, very easily. All right, I mean, simply enough by just dividing, going here, and 4 and 3. Again, I found a common factor there, divided them both by 2. There's nothing that works with the 7 and the 5, and then I got 21 over 20. You can see how that happens. 7 times 3 equals 21. 4 times 5 equals 20. Okay, and this is the answer she got here. But what she did ahead of time is she simplified by, go ahead and get rid of all of that, all those strokes there. And what she did then is she took this 24, which actually is not just a 24, but it's actually a 24 over 1. And what she did is she went ahead and looked at 7/8. So she multiplied 7/8 by 24 over 1. Okay. Now this 24 was used because it is the least common multiple of the 6 and the 8, okay, of these two denominators. The denominators of our two fractions here, okay. So when she does that, she can very quickly do this. She can cross divide here, and she gets 1, 3, and that becomes 21. 7 times 3 equals 21. 1 times 1 equals 1. Okay, and that's this part. And then she did it with the 5/6. Well, same thing. Okay, and boom, boom. This is 1, this is 4, and that equals 20, and that's this portion of the fraction. Okay, now you can indeed do this, and yeah, she did a good job with that. I wouldn't necessarily recommend it if you don't quite understand it yet, but you can indeed do it, because what she's doing, she's actually in essence dividing both of these fractions by 1/24. But then what that means is to multiply by the reciprocal, which is 24 over 1. Okay, and I'm sure we'll get back to that several more times in this unit. Okay, our next exercise is number 2 here, and it reads this way. For Anthony's birthday, his mother is making cupcakes for his 12 friends at his daycare. The recipe calls for 3 1/3 cups of flour. This recipe makes 2 1/2 dozen cookies. I don't know why she says cookies, she's got cupcakes here. Okay, I'm sorry, this is here's a little typo. Anybody else find this typo? There we go, that should be cupcakes, actually. And that's not a big deal, but anyway, let's have it be right. Okay, so yes, she wants to make 12 cupcakes for his friends at daycare. The recipe calls for 3 1/3 cups of flour. This recipe makes 2 1/2 dozen cupcakes. Anthony's mother has only 1 cup of flour. Poor woman. Is there enough flour for each of his friends to get a cupcake? Explain and show your work. And I guess she's not really considering Anthony here, but is there enough flour for each of his friends to get a cupcake? Okay, so go ahead and solve that any which way you can, thinking unit rate, of course, and come on back after you've solved it and we'll solve it together. Okay, so if I do work with unit rate here, the unit rate I'm concerned with is I want to know how many cupcakes per cup of flour this recipe makes. Okay, cupcakes per cup of flour. Why is that handy? Well, it's handy because I know she has only 1 cup of flour. So when I find out how many cupcakes 1 cup of flour can make, then I will know if I have enough. Because what do I need? I need 12 actually. Okay. All right. So let's go ahead and use the numbers that I need. We have how many cupcakes? Let's see, the recipe makes 2 1/3 dozens, so we have 2 1/3. Okay, or 2 1/3, 2 1/2. Excuse me, 2 1/2. 2 1/2 dozen cookies, and 3 1/3 cups of flour. Okay, 3 1/3 cups of flour. So if she creates her complex fraction, it's going to look like this. And I'm always highly recommending you change these into improper fractions. Much easier to work with. So 2 1/2 would actually be 5 halves, or 5 over 2. Okay, divided by, this would be 10 over 3. Okay, and again, if you're having trouble going from 3 1/3 to 10 over 3, there's just get a little extra help with your fraction multiplication and division at CK12 if you need to. Okay, so I can just go ahead and take this and very simply create my my standard equation to make it easier to work with, and it's going to look like this first. Because again, with any division problem, this complex fraction, how many 10/3 are there in 5 halves? Okay, that's what I'm looking for. And now, of course, this is going to be 5 over 2 times 3 over 10. Okay, because we're using the reciprocal. And if I go ahead and work that out, this is 1, this is 2, and then I have, what, 3/4. Okay, so we have 3/4 of a dozen cookies per cup of flour. 3/4 of a dozen, and if you know 3/4 of a dozen is 9. Okay, so only 9 because there's 12 in a dozen. Okay, again, I know we've had trouble with our conversions there, but yeah, a dozen is 12. All right, so 3/4 of a dozen is 9. And the answer would be to this question, is there enough flour for each of his friends to get a cupcake? The answer would be no, because with 1 cup of flour, she can only make 9 cupcakes, okay, per cup of flour. She can make 9 per cup, because that's the way we set up our unit rate right here. We set it up as cupcakes per cup. So we went from cupcakes per cup of flour. Okay, so when you create your complex fraction this way, whatever, it's cupcakes per cup of flour. Now, could we do it the opposite way, the other way? Yeah, absolutely can. Okay, we could have done cups of flour per cupcake. Okay, or per dozen, whatever, per dozen. This is cupcake in dozens, actually. Okay, in dozens. All right. Now, again, many other ways to do it. Could have used a whole number if you wanted to for cupcakes in dozens. Instead of 2.5, you could have used 30. Okay, right here. So you can get 30. That would be 30 cupcakes in this 3 1/3 cups of flour. Okay, right here. Different ways to do it. But if you stick with, because this is our main focus during this unit, is putting together and using complex fractions to solve problems. Okay, so if we do it that way, we come up with this answer: 9 per cup, and no, does not have enough flour. Okay, and here's our next exercise. Actually, it's a final exercise before we close our lesson, and you can go on to do some of your problem set. Here we go. Sally is making a painting. This is an odd way to say that. But anyway, Sally is making a painting for which she is mixing red paint and blue paint. The table below shows the different mixtures being used. Okay. Now, when a table is given to you like this, I'd like you to get into the habit of, and again, look what they've done. They've given you fractions here, they've given you a whole number here, they've given you actually decimal values here, okay? But when you get something like this, I want you to always think of this table in this terms. Think of this as x on the left, and then on the right, this is y, okay? Because the first question is going to be, what are the unit rates for the values? Okay, what are the unit rates for the values? And they're talking about these values here, okay? So what I'd like you to do right now, using what you've learned on deciding or calculating unit rate using fractions, complex fractions, and the like, go ahead and determine the unit rates for all of these. All right, for everyone. Take a little bit of time. That's why we're breaking this unit, or this lesson into a few days. This should be day 2. You're working on this, possibly. But go ahead and figure the unit rates for all of these scenarios, okay? All of these scenarios. All right? So go ahead and do that, and come on back. Okay, so when we come up with these unit rates, again, just making sure to make it easier on yourself, have your x and your y mapped out. And again, I mean, having it, the red paint as your x or the blue paint as your y, I mean, it's not necessarily has to be this way, but we're going to go ahead and do it this way, just so we can just practice this this routine. So if we do this here, we're always looking at we're doing a ratio as a y as a function of x. So that would be 2.5 over 1.5. And again, this is, the same, of course, as, if we did 2.5, 1.5 this way. You don't usually write ratios this way, but this is what we're doing. And again, a ratio written like this is exactly the same thing as a fraction, okay? But in this case, of course, we're creating a complex fraction, okay? So now, remember the first step we talked about is turning these into improper fractions. So then we're going to have 5 over 2 over 3 over 2. All right, so we have 5 again. How many 3 halves are there in 5 halves? Okay, that's what we're asking. That is the question we're asking ourselves. And the way we make that easy on ourselves is to go ahead and use the algorithm. 5 over 2, again, divided by 3 over 2 is the same as 5 over 2 times the reciprocal, which is 2 over 3. And again, if we do this and do this, 1 and 1, 5 over 3, which is the same as 1 and 2/3, no, 1 and 2/3. And I'm going to back up a second here because, let's see that I did this right here. Let me go ahead. So I am doing 2.5 right here, 2.5 divided by 1.5, and that is 5 over 2 divided by 3 over 2, okay, which is actually 5 over 2 times 2 over 3. Boom, boom, that equals, that's right, 5 over 3. So that's going to be 1 and 2/3. So our unit rates, and again, they're all the same, okay? The unit rate is 1 and 2/3. But what does that mean? Okay, I think one of these questions is going to ask us. Yeah, okay, yeah. So C actually, well, let's go ahead and let's start with B. All right. Anyway, the first answer here is our unit rate is 1 and 2/3. And I will talk in a minute about what that means. Okay, so that's your answer, 1 and 2/3. Okay, so go forward here. And our next question is here. Is the amount of blue paint proportional to the amount of red paint? Okay. Now, if you guys remember how that would be, the only way that this could be true here is if for every one of these in our, okay, I lost that. If every scenario was equal to 1 and 2/3, and they are, okay. Each scenario of red paint to blue paint is the same, or blue paint to red paint to blue paint is the same all the way down. Okay. Now this letter C again is to describe in words, okay, what the unit rate means in the context of this problem, which is always so important because we're always trying to establish meaning within context. Okay, so if we have 1 and 2/3 as our unit rate, the way we figured it out is remember we had our X and we had our Y, and our Y in this case was our blue paint and the X was red, and whenever we're creating these ratios, we're getting these unit rates, we're looking at Y as a function of X. So for every 1 and 2/3 quarts of blue paint, 1 and 2/3 of blue paint, there is a corresponding 1 quart of red paint. Okay, because our unit rate is 1 and 2/3 blue to 1 red. Okay, so 1 and 2, so there's 1 and 2/3 quarts of blue paint for every quart of red. So as we have actually turned this lesson 11 into more or less a 2-day affair, please feel free to go back and look over those examples over and over again. Sharpen up your skills on working with fractions, especially division of fractions. Okay? So here's our lesson summary for Chapter 11. A fraction whose numerator or denominator is itself a fraction is called a complex fraction. And we saw those come up just most recently, 5 over 2 over 3 over 2. The fraction, all as a fraction. Okay, these are complex fractions. Get used to them. Make them your good friends because they are going to be with you for a long, long time. Okay. And in the lesson summary here, also recall a unit rate. Again, this is something we've been talking about for quite some time now. Is a rate which is expressed as A over B units of the first quantity per 1 unit of the second quantity. Okay, so in the last problem we did, our last exercise there, remember we had 1 2/3 cups. Every 1 2/3, it's not cups, I'm sorry, 1 2/3 quarts of blue paint, there was 1 quart of red. So we have a unit rate which is expressed as AB. So the first quantity per 1 unit of the second quantity. That's why in this case when we're creating a unit rate, it's always going to be per unit. So this right side of the ratio is going to be 1. Okay. All right, and it gives you an example here. If a person walks 2.5 miles in 1 1/4 hours at a constant speed, then the unit rate is, and it goes and takes you through it. What we've been doing, we're 2.5 divided by 1 1/4, change those into improper fractions, and came up with our final equation here using the reciprocal, changing division into multiplication, and then getting our unit rate, which is in this case 2 miles per hour. Okay, again, this is definitely an area of our grade 7 math which is worth going over again and again. So if you find yourself confused, have questions, please bring them to me, and also go back and look over this presentation again and again. Okay, so now to finish up, complete your problem set and your exit ticket, and you'll be done. Good luck.